Thanks for the introduction and thank you all for joining. I'm very happy today to talk about my two projects, RDF Fusion and PolyArrow. And yeah, I hope you will learn something new or at least hear something interesting today. Let's get started. So maybe let's start a quick introduction from myself. My name is Tobias and I'm a doctoral student at TU Wien in Vienna, where I'm working with query engine. Yes, it's about 2 years. Research project basically led me down this path, this very happy path. And yeah, since 1.5 years, I'm using DataFusion for building these two experimental prototypes that we'll see today. Yeah, just take everything with a pinch of salt today, as yeah, some things are personal opinions, I guess. Yeah, I think it's important to start like at the beginning with this research project that I was talking about to just gather some motivation. So this is a use case that we did together with Siemens in Vienna, where we have an electric vehicle charging garage. We have 3 chargers for EVs, a battery, and a PV system to basically make this garage more renewable. And all of them have these AP sensors, which stands for active power. That basically is the amount of power that this part of the system is currently draining from the power infrastructure. And the interesting bit about this garage is this OE operating envelope here in the top right corner, which basically gives the power grid operator a way to dynamically adjust your limit of how much power you can draw from the grid. The idea is that you basically, by dynamically adjusting this limit, you can prevent grid reinforcement projects and thus lower the overall cost for keeping the electricity grid working. And so in this larger project, I had this small task of figuring out when do interesting things happen in the system. One interesting thing that we were going to talk about today is this envelope violated or not? And we can write a rather simple specification for that, basically sum up all the devices in our garage and compare it to the operating envelope. If it's bigger, we have a violation and someone should be notified, or at least it should be logged that an engineer can have a look at that and basically maybe adjust the control algorithms or something. Now with this, we had a problem that even if the violation was just for a few seconds, we got this notification and that was, we wanted a bit of a leeway. So we were looking in how can we extend our specifications in such a way that we allow the power to overshoot this operating envelope, but just for a few seconds. And a few people around the runtime verification community came up with a temporal logic for actually formulating this kind of stuff. And here you see this nice square operator, which basically means, okay, the power has to be larger than the operating envelope for 30 time units. Otherwise, we're not going to report anything, basically. So equipped with this power, we looked at a different problem, because now we don't have a single charging garage, we maybe have a second garage, and there we only have one charger and not 3 chargers. So our formula that we give this specification mechanism kind of changes, and it has to adapt to the system. And this was maybe the leading question throughout this research project, for me at least. How can we adapt these event detection techniques to the system at hand? For example, to scale that to hundreds or thousands of garages, if any operator has so many garages. But you can imagine that could apply to any other system as well. And so basically the nice thing about these temporal logics is they're talking about really a dense time domain. So you don't have these samples like you often have it in time series applications, which are great, but you have to think about sampling rates, and then you have to sometimes resample your time series. Here you're just stating, okay, it should be larger than 30 time units, let's say 30 seconds. And basically the specification monitor has to do all the things about considering the sampling intervals and that kind of thing. And here it's rather relevant because the envelope we usually get at a very infrequent, maybe once a day or once every hour, while the power systems actually change every few seconds. And so what I tried to set out to do is basically make these specification formalisms aware of the system knowledge or tailor them to the system at hand. And at the same time, often you have to actually move your entire time series to any specification monitoring program, because usually these aren't baked into your standard SQL database. And so what we also try to do is to move these monitoring procedures to the data into the query engine. But there are some things that we have to consider here where we get later to. Yeah, this is basically also the title explanation with these graphs for system knowledge, piecewise functions for actually getting the semantics of these temporal logics to work in a query engine. And we've built all of this stuff, or I'm currently building this stuff on DataFusion, which is the foundation for our implementation. Hopefully, a few people here have heard about graph query languages, so we're just going to give a quick intro, so maybe you can take something from that with you. There are two large data models. We're just going to talk about RDF here, which stands for Resource Description Framework. And basically, all our data are encoded in triples there. The triple is just a subject, a predicate, and an object. And that lets us build statements like this one here below, where a garage basically contains a certain PV system. And one interesting thing here is that we use global identifiers here, which should, in theory, basically allow users to merge these data sets from different sources and get one large data set that they can query. And also a thing that will be tricky later on is that these objects can actually be literals as well. So this could be the number 10, this could be a floating point number, but it could also be like another ID, or it could also be a date time or something. Well, with a single triple, we cannot state that much, but basically if we have a set of triples, we can visualize them as a graph. So here you can actually see the statement from before, where we have garage 1 that actually contains this PV system. And we also have a charger that is contained in this garage and so on. So these are just a set of triples that we can visualize as a graph. But now in order to extract the system knowledge, we kind of have must have a query language to actually talk to these graphs. And that's where SPARQL comes in, which is basically the standardized query language for RDF graphs. And if you've never seen this, I think it looks pretty cool. Basically, you're not querying tables here, but you're querying patterns in a graph. So here, for example, you're just interested in all the subjects with a predicate of type and an object of garage. And again, you can visualize it more like a graph pattern that you then superimpose on the graph and see where this pattern can match. And maybe now asking what has this to do with a relational query engine or DataFusion? Well, the nice thing is you can do a relational mapping of RDF and SPARQL and actually implement it on top of a relational query engine. And this is actually what many systems that are used in production also do. There are a few custom-made and a few that build on relational query engines. So we just have a single huge relation where we just put our whole graph into, and there we have subject, predicate, and object columns, and we just put all our triples in there. And a single triple pattern can then evaluate it against this relational mapping by the variables become protections. So here we're renaming the subject column to garage, and the other two become selections or filters, basically, and just reduce our table to, in this case, we're just getting this garage 1 row renamed to garage because here we have the types, but we only have a single garage in this data set. If that makes sense, we have an example on the next slide where we can basically now combine the solutions of multiple triple patterns. So here that was the example from the slide before. And here we have a second variable, and we can just join them together to actually now evaluate the entire graph pattern over our triple table. And I think this is really cool that this rewriting to relational algebra or logical plan in DataFusion works. And at the end, we actually get something that you might be familiar with, DataFusion physical plan. We do have some kind of sugar on top of the parquet scanner, but it's not much. So it's almost plain DataFusion that you're seeing here. And also very good for us because we can use the nice features that DataFusion provides. Some interesting aspects maybe really quickly about using this for RDF data. I think the most prominent thing is that you have these heterogeneous values in a single column. You have integers, you have these global IDs. You can even have like language literals with different languages attached to them. And there is this question of how you can encode it in error record batches. Because at the end of the day, we need them in record batches in order to process them. And we have actually 4 different ways of doing that. Some tend better to some use cases, while others tend better to other use cases. And that actually makes us use nested data types quite heavily. So we have structs where we store values and data types, for example, in a separate field. But we also have a large union type where you basically have a column for integers and one for floats. And yeah, it's quite exciting to actually see this work. And then there are the join semantics are a bit different if you have null values in there. Then the sorting also makes some problems because we have to, for example, compare floats and integers in the same column. And yeah, maybe what's interesting for database guys out there and database folks is that we're doing data skipping during planning. I had a quick question in Discord for that. So as a reveal, this actually works. Because we have this huge triple table, we somehow have to get statistics in order to figure out which triple pattern do we evaluate first. And then we can actually benefit from stuff like dynamic filters to prune a lot of stuff in the other triple patterns that are coming later on in the query. And so we are basically figuring out how many rows could be matching, and then we use that as a cardinality estimate to reorder our joins. And what's also nice, I think, is that this makes actually OLAP techniques like Parquet or Delta Lake that we're using more accessible to the RDF community. So hopefully getting some synergies working there. And we have a Wasm playground, which I think really cool. So you can test it out yourself after all if you want. That's basically what I did the last week. So, okay, let's recap quickly. We have now this infrastructure where we can get this system knowledge out of our graph. So we can know which devices are in which garage, but we still have to move these specifications into the query engine. And well, if you're thinking about, okay, now you're making your time series data like a function. Because all these formalisms, or many of these formalisms, are actually based on a data model of a function from a time domain to a value domain, which we will call just signals here. And this is a valid function. I think it's the sine of 1 over x or something. And yeah, good luck with evaluating x is greater than 0 on that thing. And so what we're basically doing is we only allow for a simpler but still useful subset of functions. Mostly restricting ourselves to piecewise polynomials. That's actually where PolyArrow gets its name from. And so if I have to describe it on one slide, PolyArrow, it's basically a set of piecewise signal types. So we have a regular time series. These are really just a point. So there's no interpolation between them. It's just a set of points, basically. Then we have a hold signal. You often see these step functions where the last value holds until a new value arrives. Then you have linearly interpolated time series, which you just connect them with a straight line. And then if you're fancy, you can use the more general piecewise polynomials, where you can do quadratic functions or cubic functions. For example, if you're integrating a regular linearly interpolated time series, then you get a quadratic function. You somehow have to represent the things. And the thing about these piecewise functions is they basically change their behavior at every point or at every row that we encode them in the table. So you can think again about your step function. Every time you get a new data point, your function actually changes. And the nice thing about this is you actually move the interpolation semantics into the data model with that. And yeah, we will see an example of the punctual signal in a second. And basically, we then have encodings for these different types as arrow arrays, so you can actually use them inside of the ecosystem, and a few computations defined with them. For example, you can add them, you can integrate them, and we have this nice always operator from before, where you can say, okay, this thing should hold for 30 time units. And with a DataFusion integration, so you can do that on a large batch of data, not just everything that fits into a single arrow. Yeah, here very quickly, the punctual system, for example, if you want to say when is signal 1 equal to signal 2, it's basically all the time false, just in this particular moment in time. Because here is the intersection basically of these two lines, and only here it is equal. And if you want to model the result of this computation, you basically need this punctual type to actually model that this is only an instant. And right again, a bit after that, it's already false again. And yeah, then we have this query plans where we basically have these signal semantics baked in. Most of them, they can do this resampling automatically. For example, here we have an occupancy data and a CO2 data from a building. And these have different time resolutions. But because this construct signals operator injects these resampling semantics into the data model, we can actually align these things automatically. So basically, if the data already stores this metadata on top of that, we can do this resampling automatically in the query engine, as long as we don't change the outcome from the system. And yeah, I hope I wasn't too fast here, but the question that kind of remains, okay, we have now these things and how can we combine them? So what we try to come up with is this signal annotated RDF graph, where you can basically, for every node in your graph, which represents our devices in the system, we can now attach these signals. So this could be a time series, this could be a hold signal, and this could maybe be a polynomial signal. So we just attached it to it, and then we have a query engine where we can extract the nodes from the graph, as you've seen it earlier, and then extract the signals from the graph based on the results from the pattern matching down here. For example, here we're getting all devices in the garage again, and then we're getting the active power signal from the device. And then we can just maybe we can just sum up all these signals together, compare them to the envelope of the garage, and once that becomes violated, we trigger our event and present an alert to the user. The idea is then to just plug in your temporal logic specification in there. Because you have these functions inside the data model, the semantics of these temporal logics can be mapped to the signals. And yeah, I hope I didn't take too long or wasn't too fast. I think we've seen two rather exotic projects now based on DataFusion. I hope you've learned something new. If there was something I didn't explain very well, I'm happy to go over it again. And yeah, we have this playground. I'll just post a link in the chat afterwards, so you can play after the meeting a bit with SPARQL if you want. And yeah, there are many, many things that I would like to look at in the future. And to all the contributors that made that possible, thank you from my side. Yeah, that was it. So if there are any questions, very happy to answer them.
I would love to hear more about your, since no one else put questions in the chat, I'm just going to voice myself upon you. I'd love to hear more about your join reordering scheme that you described, right? Where it's cool you sort of done the mapping of RDF into a bunch of self joins, but then you describe you have to like order the joins based off. I'm not exactly sure what you do off them. So I'd love to know like how you do that and what the mechanics are and what, if anything, you would have to say.
Yeah, that's a very good question. So what SPARQL or engines or RDF store usually do is they materialize this table in different index permutations. So if you have one that starts with predicate, then subject and object, then you have one index that starts with object, then subject and predicate, and so on. The idea is that if you have like a triple pattern, it kind of depends which components are bound. Basically, this determines what is the best index to scan. And now we have our default storage backend, if you can call it that, is based on Delta Lake. So we store these SPARQL files in an object store. and we have one large operations table where we are just streaming in the inserts. And then we are materializing also 3 tables with these different sort order permutations. And so now when we have these query patterns, for example, here we could figure out, okay, the index that starts, or the quad table that is sorted on subject or on predicate, and then object will be very good for pruning the results for this thing. And then depending on how big your row groups are, you actually get a quite reasonable estimate, at least to the page size. If you have the page size index enabled, you get a quite reasonable estimate for the cardinality for this triple pattern. And then you do the same thing here. For example, if we have a subject bound to garage 1 and 2 variables, then we would choose the quad table that is first sorted on subject and basically then do the pruning. And I think DataFusion has this nice capability where you can give it a half-baked Parquet access plan, and then it can refine that during processing, so we're not even doing the work twice. And yeah, then we can still use dynamic filters and all that nice stuff that actually is quite important for some queries here. Does that make sense? I hope I...
Absolutely. It's cool to hear you talk about these features, right? Which I never know working down in the engine whether or not they get used outside or whether they're just internal engineering. Like we kind of design it with the hope that other people can use it, but you never really know until you hear about it. So I'm glad. It's kind of cool to hear like a use case that's using it.
Yeah, perfect.
Yeah, amazing work, Tobias. Thank you. Any other questions for Tobias or comments?
I mean, maybe I can quickly show the demo if you want.
Yeah, we have a few minutes. Yeah, if there are no questions, that'd be great.
So can you see?
Yeah.
Yeah, so I've played around last week with actually getting this thing to compile for Wasm, which wasn't on DataFusion that it didn't work, but on my side. But basically what you can do here is select a version of RDF Fusion. So we store this basically as a JavaScript wrapper or a glue code and a Wasm binary on an object store. And you can just download them into your browser, or you just upload your local build if you want. And then you can do stuff like configuring DataFusion here. I just put some interesting settings there. And then you can select the data set. Again, this is stored in our object store. For example, this is a it's a well-known benchmark on SPARQL queries. And we're basically now querying a Parquet file that is stored first on the graph. This you can forget, it's basically another component in a quad instead of a triple. And then it's sorted by predicate, then object, and then subject. So queries that bind the predicate to a fixed value will be performed on that. And I've uploaded a very small, let's just stay with the Spider-Man dataset that just had a few triples, and I've uploaded it locally. And then you basically create your DataFusion and RDF Fusion instance, and you can click on run, and then you can inspect your logical plan, your optimized plan, and so on. And actually everything except for the object store surfing runs in your browser. That's really nice. So thanks if everyone is here to make Wasm work on DataFusion or for DataFusion. Really great job.
Oh, cool. Thank you so much.
Right on. Very cool. Thank you, Tobias. Doesn't look like there are any.
Thanks for having me.
Yep, appreciate it. Alrighty. I guess now is a good time to transition to Jerome. Take it away.
Thank you. So do you see my screen?
Yes.
Yeah. So I'm Jerome, working at Cloudflare on R2SQL. This is what I'm going to showcase, how we actually built the product we call R2SQL, still open beta, soon to be GA'd on DataFusion, and also on the Cloudflare infrastructure, which I think is interesting as well. So yeah, I'm a principal engineer at Cloudflare, working in what we call the data platform. And I've been working on R2SQL, on many other data-related projects. So R2SQL is our serverless distributed query engine aimed at data that's stored or that like registered in Iceberg catalogs. And of course, Cloudflare, which could be described as a global network, practically everywhere where there are humans with internet connections, we have a presence there. And this is the network that we use to actually host what we call our dev platform. So the dev platform is an ensemble of products aimed at developers to facilitate the implementation, hosting, and maintenance of applications that are connected to the internet, hosted on the internet, stateless or stateful. So there is a large palette of products there, and R2SQL is one of them, right? But it's not only part of the dev platform, it's part of the data platform. So the data platform is a sub-ensemble of products at Cloudflare that all work together to actually create a user-friendly story around data ingestion and data retention and data processing. So I'm gonna talk a bit about that. So yeah, what is the data platform? So the orange box there, this is what we're gonna talk about, how we built that on DataFusion, right, R2SQL. But in order to have data that you query, you need to ingest it. So this is the job of the data platform, really. It starts at the pipelines product, which allows you to define streams of event and then their schema, and then send events either via an HTTP API or through Cloudflare workers binding with high throughput. It's going to be validated and aggregated and put in Cloudflare's object storage, which is R2. So it's essentially S3, but at Cloudflare, right? You can think of it that way. With the nice benefit that egress on R2 is free, which is great. And right, once you've aggregated your data in R2 through pipelines, you can, this is optional, but you can actually register that data as Parquet files in an Iceberg catalog. So Iceberg is a way to actually track all your data files, their schema, when you've written it, some metadata about it, statistics mainly, in a way that's then able to be leveraged by query engines like R2SQL in order to actually make querying that data possible efficiently, even though it's on object storage, which is not like as fast as an SSD, of course, not the same latency profile there. So yeah, great data platform, still quite fresh, right? Not every product there is GA'd, but it's still great to use. So I encourage you to try it. So now let's talk about R2SQL. So this is the infrastructure schema, the very high level infrastructure schema of what R2SQL actually is, through the prism of like a SQL query, right? How do we receive it? Where do we process it? Where do we fetch the file? So starts at the left with what we call the eyeballs, which is the user sending an API request to a Cloudflare worker. So worker is practically the entry point for all Cloudflare product because of its versatility and its speed. And this Cloudflare worker is responsible for the identification of like authentication, of course, right? But also once all that's done, deciding where to actually run the query, forwarding that query to a compute node that takes the responsibility for that query now, and it's going to be that node that is going to see that query run through completion, right? And if not, report the error to the worker and to the user if there is some error. And so the compute nodes, there are 4 of them. There are many of them actually. Every point of presence of Cloudflare has many, many machines running R2SQL as a service. And so, yeah, this is basically running on the whole of Cloudflare network. So there is a large distribution there. The entry node is going to take responsibility for that query. It's going to ask DataFusion to inspect the query. We're going to see how it does that. Connect to the R2 data catalog down there to get the metadata about the tables that this SQL query actually refers to. Then it's going to fetch the Iceberg manifest. So I'm not going to explain exactly what Iceberg manifests are, but it's a way to register Parquet files basically with some stats, okay? And once the compute node is satisfied, like the tables exist, the schema that we can infer from by looking at the query actually makes sense relative to the tables we have. We are convinced we can execute the query. Then it's going to, of course, emit through DataFusion an execution plan. And it's going to start dispatching that execution plan through the network. This is the network boundary there, to other compute nodes that are exact copies of this one. Those are going to be crunching the numbers, fetching the data from R2 through an IO cache in order to be a bit more efficient in terms of IO, communicate between them, and then formulate the answer and have an API ball in the end. And all that data crunching is, of course, powered by DataFusion. So there are many challenges, of course, in coming up with such a system. And I've picked some of those, the ones that seem to be the most relevant for the talk. And I'm going to try to convey what they are and how we overcame them. So I think you all know that DataFusion is not designed to build distributed systems. Like it's nothing prevents it, of course, but it's not shipped with tools or libraries that are going to make that possible out of the box, right? And of course, as you can tell, like we needed distribution there. The reason we needed distribution is to solve one of the challenges that was the most prominent one, because of the type of queries that we wanted to be run on R2SQL, which are analytical queries. Those queries tend to be very large, like crunching a lot of big tables. And so the only reasonable answer we had to that, besides scaling vertically, which is not really what Cloudflare likes, like we like payloads that can be spread as much as we can in order to absorb the load through the infrastructure. We don't like very, very tall vertical scaling. So in order to get the CPU to process those queries, we actually needed a solution to distribute. And we found that solution almost ready to use in an open source project called DataFusion Distributed. When we started using it, it was not under the DataFusion contrib, and now it is. So it's a great signal for us. And also, it's I want to give a shout out to Gabriel Gabotex, because he's been like he's the key person there making this happen. That library is actually very, very great. Like it gets almost everything right, at least for us. It was really a pleasure to use. And so the great things about that library is that in the end, you still end up with a DataFusion plan. So it's not like yanking something like yanking the regular DataFusion plan and plugging something exotic. It's still the same DataFusion plan, except that what makes it distributed is that what DataFusion Distributed actually does for you is going to find the partition line inside your plan, and it's going to inject in the plan, it's going to inject operators that are going to be responsible for communications between the nodes. And of course, there is logic there in order to make sure that what's being scheduled in the end is sensical and correct, of course. But in a nutshell, this is what it does. It finds the distribution lines, and it fans out there. It introduces the node that allow the fan out there. And what was great as well is that it doesn't mandate any kind of transport for that communication between nodes. So we're actually able to plug all the Cloudflare goodness with our great network primitives there to make things super efficient for us. Second challenge, memory heavy, right? Analytical queries are memory heavy, not only CPU heavy. They're even more memory heavy than they are CPU heavy, to be honest. And RAM memory is something that's costly and like scarce under every, like compared to actual storage on R2, this is going to be many times less abundant than the storage of the database itself. So there were critical challenges there that we had to solve, like namely joins. How analytical query tend to be very join heavy, and those joins themselves tend to be very heavy on very large tables. So with a finite amount of memory per node, we needed to be able to actually run stuff that we couldn't on a single node, of course. But also we need, and this is the actual difficulty, because if it was only, we cannot run it on a single node, let's distribute it. That's not the whole solution, because that solves some issues, but some operations need to actually concentrate more data on a single node, even when it's distributed, than what the node can hold, right? And this is where you are in trouble. So we implemented actually 3 countermeasures there. We estimate the join cardinality as well as we can using the stats that we have in Iceberg, and also stats that we continuously enrich from the data that we can see is put in the Iceberg. This allows us to accurately predict the cardinality of joins, the cardinality of the intermediate results of joins. It also allows us to order them in a way that minimizes that cardinality. So this is, this is a lifesaver for us. And also the second goodness that comes out of estimating the join intermediate cardinality is that we are actually able to pick the right join implementation according to the compute needed and the compute available on the infrastructure, right? So there are joins, for instance, that cannot be spilled. So this is the third optimization. I'm going to come to it. Some joins cannot be spilled. Some join implementation cannot be spilled. We need to identify that and swap the fast implementation of the join with something a bit slower, but that actually can spill, right? The third countermeasure there is spill to disk. I think this is nothing new, right? But we implemented it. It worked great for our purpose. So yeah, I wanted to mention it. Yeah, query latency and I/O. This is something a bit less important for analytical queries, but you still want to minimize it, right? So there are many users using R2SQL not for analytical queries, but for other purposes, like even sometimes in interactive speed scenarios, and we actually support that as long as the query allows it, of course. So we want to minimize the latency. What did we do to make that happen? Well, we read as few bytes as we can, because the fastest reads are the ones you actually don't do, right? And so we aggressively prune the search space, the scan space using, again, the Iceberg table statistics. We actually wrote our own table provider to make that efficient for us. And then we try to go closer to the data. Catchphrase here is forwarding the compute, at least on Cloudflare, is way cheaper than actually forwarding the data across the world, right? So if you are in Europe, your bucket is in Australia, you might want to compute the query in Australia and just return the results, right? Because otherwise you're gonna have many transcontinental and transglobal connections that are going to slow things down considerably. So this is a native characteristic of Cloudflare. We can actually forward traffic very easily and have it processed where we think we should do it for whatever reason. Here, it's to be closer to the bucket. And then we, of course, leverage the cache as much as we can. So what we cache is the IO, not the results, of course. And Iceberg actually makes that super easy for us because every data that you plug in Iceberg can be mutated, but we are guaranteed to never read stale data if we follow the Iceberg snapshot. So the snapshot actually tells you what the set for that atomic commit of data on the catalog. Iceberg can tell you this set of files are the ones that comprise the coherent set of files at that instant in time. And following the links in the snapshot, we can actually read a coherent view, even though most of the data is cached, because as soon as it's replaced or superseded, the Parquet file that you read like 1 week ago, you won't have it in the snapshot anymore, and you won't actually try to read it again. So that makes things super cacheable for us, and it accelerates things quite considerably. Just to illustrate what I meant by pruning the scan space, let's imagine you have that query at the top, right? It predicates on price and timestamp, and it orders on timestamp. So R2SQL is going to query the R2 data catalog for the snapshot, get the schema, the partition key, the manifest list that contains the Parquet files, the lead that mentions the Parquet files, sorry. We're gonna have a look at the Parquet file in that manifest, and we are going to see, because there are stats inside the manifest for every Parquet file, here for every partition, but that's a detail. We are going to see that, okay, I have one predicate on timestamp, and it turns out that I know that this file contains only data for like that date. So I can disqualify those 2 files, and I need to actually scan those 3 because they might contain matches. And now we actually open those manifests, they contain Parquet files as well, and we have a look. And again, we have min-max stats for every Parquet file, and because we have a predicate on price, we can actually tell that the files that might contain something are those ones. And of course, we are not going to read those ones, those Parquet files. So over the number of manifests that you can prune and the number of Parquet files that you can prune, like it adds up to, I don't know, 95% of your data set that you end up not reading. And this makes actually the thing, this makes R2SQL possible at all, right? Another challenge, big one, like how do you consider operations on a massively distributed system? So a query can actually enroll a many great amount of compute nodes depending on the size that we think the query requires. And so at any point in time, you can have query running on many nodes at once. And the reality of rollouts of updates at Cloudflare is that the network is so vast that it's not instant. It takes a long time, right? It can take many hours. Of course, we have emergency procedure to make that much faster, but like we don't, like the day-to-day operations, not an emergency procedure. So we have to compose with rollouts that take a long time, right? And of course, you update every machine at once. And this is not a random process, but you can, as a service operator, you cannot really control it, right? So what we need to do, and also the important thing is that DataFusion between 2 major versions is not compatible with itself, okay? Like nothing guarantees that the plan that you emit with DataFusion 52 is gonna work with DataFusion 53, like and for good reasons, right? But this is a massive issue for us because now, if we were not careful, we could have queries planned by the DataFusion 54 trying to be run on a DataFusion 53, and boom, that just blows up. So you could actually track that and mitigate it in code, but there is another solution which is much easier and much safer. You try to actually separate the versions that are running on your network while you are rolling out a new version as much as you can, so that you have the close to guarantee that no two different DataFusion version, or even two different R2SQL version, are going to be running on a single query at once, right? It's always one version that works on a query. So the way it works is those cities I mentioned where we are in every part of the world, like we call that point of presence. And what we end up doing is we are draining traffic to point of presence, rolling out that point of presence completely, and then we are taking back up the point of presence. So this actually is the biggest safety we have there into the route, which kind of guarantees that no matter what, you cannot have two DataFusion or two versions of R2SQL talking to each other. And there is a second layer of protection there. Let's say there is a bug and the rollout doesn't work as expected. The system itself has the knowledge of all the other nodes that are running and their version and their characteristics, and it's actually able to steer away from nodes that it doesn't recognize as compatible. And the service that we use in order to do that is like HashiCorp Consul's service discovery. It works great. So those are the two layers that we put in place to simplify ops while rolling out updates on the distributed system. And there is a third one that is the last line of defense. When something goes awry and a node actually detects that it won't be able to plan because the point of presence is supposed to be drained, but it's still serving traffic somehow. But it lands on a node that is like very, very close to have 0 instances of its own version in the point of presence. That could happen. It couldn't schedule a query, right? Like it wouldn't have enough nodes available to schedule the query. So what's going on then is that we are actually able to detect the case and reroute transparently the query for it to be run somewhere else. It's not going to be as fast because it's not going to be the point of presence that was closest to the bucket, but it's going to be practically invisible. Now, some good stuff that we implemented on top of DataFusion to make things faster for our use cases. So we implemented late materialization optimization pass, or optimizer really. And what it does in a nutshell is when you do that kind of query where you select star, but then you predicate on few columns, what you can actually do and what that optimizer does, it recognizes the pattern and it's going to be able to scan only the predicated columns. So it's going to read way, way, way less data than if it had to read star, of course. And then at the last minute, when we actually compute the top 100 in that case, for those 100 rows, we are actually going to go ahead and pull up those missing bits of data that we haven't materialized up to that point, which is why it's actually called late materialization. So this is a great way to reduce the I/O. Second thing we did, so the top K filters, like when you have, I'm going to showcase that on the next slide, but basically we made sure that we could stop as early as we could while scanning a table and there were predicates and top K, so that we don't have to read the full extent of the rows that would qualify to know that we can return. So we can actually return early. This is what that optimization does for us. And like picking the right join implementation and being able to reorder the joins in a way that's informed by those coordinate estimations. This is also passes on the plan that is actually annotated by the coordinate estimator. And then we feed that actually into the DataFusion own rules to let, like most of the time, DataFusion picks the implementation we want, and this is what it does for us. Yeah, so the top K optimization I was mentioning very briefly. So this is familiar. We saw that on the previous slide, right? So you recognize we have those parquet. We know that we need to filter them. And what we're going to do now, we know that we need to read 2, 3, 4, and 5. We are going to order the scan, actually. We are going to order the scan in the order of the query. And if it's if it's ascending, we are going to order the files ascending. If it's descending, we are going to order the files descending. We can do that even when there are many columns. Right? It doesn't matter because we have the stats for that. So we are actually able to know beforehand what Parquet files are the most likely to contain the information we are looking for first. And so we actually scan in that order according to those stats. And this is actually illustrated there, right? So we start, this is the execution order. So this is the real time, the word time, and this is like the ascending value of the timestamp, so the order close. And you can see we start reading for that parquet. We find a predicate match there. So this is match 1.1, find another one here, find another one there. So 3 rows match so far. We need 5 rows to satisfy the query. So we know that we have to continue, right? Next in line is parquet 5. So we find match 2.1, 2.2, 2.3, and 2.4. And when you look, we actually have more than 5. Now we have what, like 7? But the 5th best match actually is higher than the next parquet minimum value, right? So we still need to look. So what is the 5th best one? 1, 2, 3, 4, it's this one. This value could still be replaced by something that's in this parquet because that parquet minimum value is actually lower than that match, right? So we know that we still need to read that file. We actually do, and good thing we looked, we found a match that is actually better than the 5th best. And now, because we know that the maximum value of that, the minimum value of that next parquet that we will have to read is actually higher than our worst match. We have proved that there cannot be any better match in our top 5 there. And so we can actually return there, we can stop reading. And this is something we implemented. And because most of the early queries we had on AutoSQL, because we didn't support join immediately, were simple filter scan queries, this had a tremendous impact on the perceived performance of the system. And yes, this is all I have. Obviously, there are many, many more challenges. I couldn't fit everything, and there are many cool tech things that we had to implement in order to make this work. We have another talk scheduled in a couple of weeks, I think. It's going to be my colleague Sergio. And I think, yeah, we will have then the opportunity to go into deeper details. So do you have any questions?
Awesome. Thank you for the talk, Jerome. The chat is full of questions. So I don't know if anyone wants to like unmute and go. Tim, maybe you asked your first question. Maybe you can start and we'll just go down however many we can get through in the next couple of minutes.
Sure, yeah, it's a quick question about how you designed the distributed layer here and whether DataFusion Distributed actually supports sufficient generality in the transport layer that you could use object storage rather than sort of peer-to-peer communication. Relevant because I'm sort of exploring serverless compute backends and haven't found something that immediately works for that case.
Right, so you're asking whether the protocol for the transport is going through object storage in order to write intermediate results?
Whether you could, if it's sufficiently abstract or general that you could do that.
We could do that, and as a matter of fact, so DataFusion Distributed has many, comes out of the box with many great things. One of them is it handles the serialization for us, and it has its own protocol So we didn't have to do that, fortunately. But at the core of it, what actually transits between nodes, most of it is Arrow IPC, and you could totally serialize that on object storage and use that as a basis with some metadata for your communication, right? It doesn't have to be streamed, but peer-to-peer. You could have a storage, intermediate storage, yes.
Thanks.
How do you handle write concurrency with Iceberg? This was Adrian's question. Yeah, so this is on R2 data catalog, right? This is the other product I mentioned. So the way it works is at the core of it, you have a transactional database that is actually able to hold a lock on your current state of your Iceberg warehouse. And what happens is when you actually want to write a new version, a new snapshot, you're going to come knock on Iceberg's door and say, hey, I just wrote that snapshot, please replace previous snapshot, which the ID was 1, 2, 3, 4 with the new one, which is 4, 5, 6, 7. And in the meantime, somebody else wrote, and we can actually identify that, like the service actually identifies that because we lock the, we have a transactional lock on the table. It's a Postgres really. And we are able to identify that that snapshot would overwrite a snapshot that has been written in the meantime and reject it. And we can also detect like the case when two writers are committing concurrently because again it's a lock on the on a real Postgres table at some level. ClickBench Q24, yeah.
Oh no,
Sorry,
yeah.
can
So
I ask a clarifying question?
Yeah, sure.
So I mean that makes sense. But what I'm wondering is how that sounds like kind of like optimistic concurrency. Like you assume there's no concurrent writers, and if there are, you reject it and try again. But how is that able to deal with, like, I don't know, thousands of writers at a time?
It's not. This is a real problem. So there is contention, first of all, and then the optimistic writing, it does create that kind of issue where you are continuously being bounced by the Iceberg warehouse. So this is something we are actually working on to mitigate. This is not an R2 data catalog defect as much as it is how it's supposed to work for the the Iceberg warehouse. Like this is how it's designed to work. But yeah, when you have a very high frequency write and your write tends to be very long before you commit them, then yeah, it's going to be an issue. Fortunately, like the pipeline that does most of the ingestion on our platform is very good at avoiding that. So yeah, if you have external writers, that could definitely happen.
That makes sense. Yeah, I was wondering if you'd solved it like externally or within the catalog, because I imagine if I spin up, Cloudflare workers and try and do inserts from each one of them, that's problematic. But thank you.
Right.
I would like to pass 24. I was just pointing out that has the same pattern that you described of late materialization, and so we've been working on it to try to make it better in the core. That was basically my whole point.
Oh wow. Yeah, well, that's great because like every optimization that DataFusion comes shipped with, we can actually remove it, which is less code for us. We have actually contributed some stuff to DataFusion already. Like I think some have been merged, some are still in flight. But yeah, this is good to see the community filling those gaps.
Thank you.
Yeah, I think it's actually the exact same optimization the DataFusion core has. I don't know where we are at with like dynamic filters and DataFusion distributed, but I imagine if you were able to pass the existing DataFusion dynamic filter across the wire, it ends up being the exact same thing that you showed on your slide.
You have to if you turn on filter push down into the Parquet scan. That's the key.
Right. Yeah. Good point.
Right. In our case, there was the added complexity that DataFusion discrete is in the way, and whatever you do, you need for it to be able to actually represent like the thing through the wire. And this is why we ended up having to code stuff that maybe we can do without, but this actually worked for us and we were able to optimize it for our use case. So we just went and did it. Yeah, we have our own table provider. Is that using the early stepping? No, it's not. Yeah, this was the question. Yeah. Wow, it's becoming hard to track. Like, are there other questions that you would want me to answer?
How about I can read them, if that would help, so that you can focus on answering them. So one question we haven't gotten that Daniel asked earlier was that how do you handle non-recoverable failures for big queries in DataFusion Distributed, other than like fully retrying them?
We don't. We fully retry them. So it's very difficult to carve out the failure scope of a query in a way that is going to not be crazy complicated right now. So we just recognize that the easier thing to do is to retry the query. For most queries, this is okay. They are not running for hours or even minutes, right? But for some of them, it could be an issue. And when it actually becomes an issue, we will need to find a real solution for it. But this was not necessary at the time.
It looks like maybe the last query that we have here, we're almost out of time, is from Samyak, who asked, how do you handle concurrent queries on the same node since they will compute for CPU? Do you have some kind of scheduler or a guard on how many queries can run in a node?
Right. So the answer is going to sound lame and cool. I think like the compute pool of Cloudflare is so vast, really so vast, that for now we don't really have to worry about that, which is great. When you can consider your compute pool infinite, this is the best, right? So it's not infinite vertically, but you can consider it infinite horizontally, which is what we currently do. Not totally, there are mitigations, and we are actually building awareness of the load of nodes, because we know that soon this is going to be less and less true, right? As the usage picks up. But for now, we don't have to mitigate that at all. When we do, this is going probably to take the form of a solution that's going to be based both on console service discovery, where we can actually register like close to real time various parameters of the load of systems running on the infrastructure, and another system that is going to be able to tell us higher level stuff like who is computing what for how long on what node, and then have the router not just like shuffle stuff around, but be able to actually steer the traffic where we do know that we are a bit idling. And this is not yet done, but this is design. Like we have stuff to do that, just wait, we didn't need to push that button yet.
Awesome. Thank you. So thank you so much, Wyatt. Do you want to maybe wrap up? I know we're already a couple minutes over time.
Yeah, no, great presentations, both Jerome and Tobias. Thanks so much. So we have a bit of a break until our next showcase. We're taking the Thursday off before Labor Day, so I think we'll be back together on the 17th of September, also a Thursday. Time TBD. But if you follow the thread in the DataFusion repo, we'll keep you posted. And then this recording will be posted this afternoon if you'd like to revisit either of these great presentations. So yeah, appreciate everyone joining, and thanks again, Jerome and Tobias.
Yeah, thank you all very much. It's been great.
Yeah, thank you for having us.
Thanks.
Bye.
Take care.